Let's revisit how we draw and use quadratic curves. The simplest quadratic function, the parent function that is f of x equals x squared. And if we try to plot this function and take some values of x, let's say starting at -2 and ending at 2, f of x, which is x squared, equals 4 in this case. -1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. And next, we can go and plot these on the Cartesian plane, and we get those points. Now, if we connect these points by using a smooth curve, we get this kind of function. You should notice that this is a smooth U-shaped curve, and this smooth U-shaped curve does not contain any corners, no sharp corners, and no straight line segments. It is called a parabola. But the word parabola is reserved for the curves of quadratic functions. So not any U-shaped curve is a parabola. Furthermore, this curve is a symmetric curve. It has an axis of symmetry, and in this case, it is the y-axis. So this curve is identical to this curve if you fold across the y-axis. And this axis of symmetry passes through a point that we call the vertex. Because this parabola is concave up, i.e. it opens upwards, the vertex is a minimum. It's the minimum value that the function takes, and it's the minimum point on the graph. If we consider another quadratic function a bit more complicated, and we try to plot it, let's take values from -4 up to 3. And if we calculate the values, we'll just do 1. Let's do -4. When x is -4, f of -4 equals -4 squared is 16. Mind you, the -4 is all squared, plus -4, which is -4, minus 6, and this equals 6. And if you do this process for all the values of x, you get 6, 0, -4, -6, and another -6, -4, 0, and 6. Now, if you plot these points, that's the way it looks. Now, you can see that it makes an outline of a parabola, but it's very interesting that here, if you connect those 2 points, it might seem that you'll end up with a straight line segment. Now, we know that a quadratic is a smooth curve. There are no corners and no straight line parts. So in order to get a better view, we take another point right in the middle here. So we take, let's say, x equals -0.5. And if we do the calculation, we find that the coordinates lie here. And now it looks that we can actually draw a smooth curve through these points. And if we do that, this is what we get. Again, we get a smooth U-shaped curve. Again, it is concave up. It is symmetric, but this time the axis of symmetry is at x equals negative 0.5. And we can use this curve to solve equations. For example, consider those 2 points. Now, if this is y equals f of x, then at this point, y is 0. So, what we can read from the graph is f of x equals 0 at x equals negative 3. So, this is a solution of the quadratic equation, which is x squared minus plus x minus 6 equals 0. And the other solution is this point, which is 2. Those 2 points that cross the x-axis are called the roots of the equation or the zeros of the function. The word roots has nothing to do with square roots, and the zeros of the function refers to the fact that when x is negative 3, the value of the function is 0. So if you have a graph, you can easily solve a quadratic equals 0 just by looking at the point where the curve crosses the x-axis. But that's not all. You can solve other equations as well. Let's say we want to solve f of x equals 6. This is 6. That's where f of x equals 6. And we look at the place where the value of y is 6 on the function. So we have this point and this point. Here, x is negative 4, and here, x is 3. So the answer is simply by looking at the graph is x equals negative 4 or 3. And as you can imagine, there are millions and millions of solutions on this curve because there are millions and millions of points. Let's take one more. Let's say we want to solve f of x equals 10. That's where the function equals 10. And we have to drop a perpendicular. And obviously, we will have to estimate our answer. So the advantage of the graphical method of solution is that the graph is very easy to use, but in most cases, you will have to approximate your solution. And obviously, we're somewhere here around 3.5, something like negative 4.5, but we can never be exact. Let's look at another function. G of x equals negative 2x squared plus 4x minus 3. And without going through the details of calculating g of x, let's draw it right away. And this is what we get. Now, what's interesting in this case is that the curve is concave down. Again, we have an axis of symmetry. In this case, the axis of symmetry is at x equals 1. And the vertex in this case, because it's concave down, the vertex is a maximum. It's the maximum point on the curve. There is no value that is higher up. It is also to be noted that there are no roots, i.e., the curve does not cross the x-axis. So, f of x equals 0 has no real solution, cannot be solved. But even then, a graph such as this one can still be used in conjunction with another graph. For example, how about solving f of x equals g of x, where g of x is our quadratic and, sorry, those should be h of x equals g of x, where g of x is our quadratic and h of x is a straight line given by x minus 4. We only need to look at the points of intersection. And this looks something like negative 0.3. And this looks like something like 1.7, more or less. Of course, if we do a good calculation by equating those two and solving them by the formula, you'll probably get a better accuracy. But again, in this case, we can use this curve and this line to solve g of x is greater than or equal to h of x. So we want the curve of g, which is the parabola, to be higher up on the y because it's greater than. And all we need to do is just look at the curve. That's where they are equal. And here, g of x is higher up. So g of x is higher up for the interval from negative 0.3 to 1.7. And simply using the curve gives us negative 0.3 is less than or equal to x, which is less than or equal to 1.7. And that's it.